Swayam Prabha. Digital India. Educated India.
So in this lecture, I want to continue the discussion on coating and derive a very classical equation in fluid mechanics called the Landau-Levich equation. Now, I'm showing you two figures. They appear very different problems, but hopefully I'll convince you that these two problems are intrinsically related. Now, on the left panel, what you're seeing is a bubble, a gas bubble, displacing a viscous liquid as it moves through a tube. And this problem was first addressed by Professor Bretherton in 1967 in Cambridge. Now, we've already seen the Landau-Levich flow on the right hand side. It was done in 1941, but Professor Bretherton wasn't aware of the work of Landau-Levich when he first did it, and he derived a result which is very similar to what Landau and Levich derived, but there are subtle differences. Now let's focus on the Landau-Levich flow. The Landau-Levich flow has, as I already said, you can divide the flow into the meniscus into two parts: a static meniscus, which I'm showing in red, right? When you go far away from the plate, it is the static meniscus, but when you come very close to the plate, the viscous drag causes the interface to change its shape, and you have the dynamic meniscus as you come close to the plate. Now, in the same way, if you look at the Bretherton problem, let's look at the region close to the plate. Let's focus on this region, right? If the bubble is moving to the right, then it's more convenient to make the bubble stationary and analyze the problem in the frame of reference of the bubble. And when we do that, the bubble becomes stationary. It will appear to us that the tube is moving backwards with a velocity u, right? And when we look at the meniscus in this region, that's shown in the box. So you have the plate here. This is the surface of the tube. It's moving to the left in my figure. And then now you have the meniscus. That's the shape of the bubble. So this is the shape of this is the bubble here. This is bubble. This is the liquid. And note that this problem is strikingly similar to the Landau-Levich flow. The only difference is that the figure has to be rotated by 90 degrees. But there is another very important difference. In the Landau-Levich flow, we have gravity. Here, you can ignore gravity because it's a horizontal motion. Now, what does gravity do in the Landau-Levich flow? It sets the curvature in the static meniscus. The curvature of the static meniscus is 1 by LC, or the radius of curvature is LC. Whereas, in the Bretherton problem, the curvature is nothing but is given by the radius of the tube. So in other words, it's assumed that if you're away from the walls of the tube, then the shape of the bubble is largely a spherical cap. Okay. So in other words, if you think of this as a thin tube, then the static meniscus would be a spherical cap whereas the dynamic meniscus would deviate from the spherical cap and you get a thin film. Okay. Bretherton's analysis is slightly different from the Landau-Levich analysis on these two counts. One, you do not have gravity, right? And two, the meniscus curvature is the radius of the tube rather than the capillary length. So if one were to do exactly the same analysis as the Landau-Levich flow, then the thickness of the coating that you would get, now the outer region or the static region is given by the radius of the bubble, radius of the tube. This gives us 1.337 capillary 2/3. Recall that the same analysis for the Landau-Levich flow gave us H by LC 0.9458 capillary 2/3, right? Now, one of the things that I want to do in this lecture is to derive the so-called Landau-Levich equation. Now, how do we go about deriving this Landau-Levich equation? What exactly is the Landau-Levich equation? Now, in the previous lecture, we basically did a scaling an estimate of various terms when we basically balanced the forces in different regions, right? We did not have an exact expression for the curvature in the dynamic meniscus. Now let's look at this region more closely. So here's my dynamic meniscus. This is an amplified view of the dynamic meniscus. This is my plate moving with a velocity of u0. And my interface in the dynamic meniscus would be something like this. So this dynamic meniscus, remember, will match the fully developed coating far upstream. And therefore, far upstream, you could basically have a uniform flow. Why would the velocity be uniform? Because you have no slip on the wall. Therefore, the velocity should be u0 on the wall. But at the same time, once the interface becomes vertical, meaning parallel to the plate, then the stress, tangential stress is also zero. The tangential stress, essentially in this case, zero would mean that there is basically the velocity profile is flat. Okay. So if the thickness of the coating is h infinity, then we know that the mass flux that is going through the coating would be velocity u0 h infinity times rho. This is mass flux per unit depth. Okay, this is a two-dimensional problem, mass flux per unit depth. But if I'm somewhere away in the dynamic meniscus, then I can have a velocity profile which is varying with distance away from the wall. In this case, the velocity profile would be something like u of y. Okay, if you remember, we've said that my coordinate system is y is basically perpendicular to the plate, x is along the plate. Let's start with the normal stress balance. The normal stress balance is minus P plus tau Nn. That's the normal component of the deviatoric stress, will be surface tension times curvature, right? But we also have if most of the flow is parallel to the plate, then the dominant velocity component is u as a function of y. So therefore, this term which is tau and n, would be very, very small. And this gives me pressure P will be surface tension times curvature, and this, in this case, the curvature is just sigma hxx. Okay, please correct this. This should be gamma times hxx, and this gives me the pressure gradient, which goes like gamma times hxxx. If we substitute this in the now x component of the momentum equation, minus del p by del x plus mu del square u by del y square 0. Okay, so we have made a bunch of approximations in writing down the x component of the momentum in this fashion. The first thing is, we've said that the Reynolds number is very small, therefore all the inertial terms drop out. We've also said that the dynamic meniscus is so thin that gravitational effects are not very important. And the third point that we're making in this equation is that all the viscous stress, all the shear stress is because of the term del square u by del y square. Del square u by del x square is very, very small compared to del square u by del y square. This is the lubrication approximation, right? Now, if we have this, I have this equation here, and from this I can basically get, if I say that the velocity is a function of y alone, I can write it as a total derivative. The pressure gradient is primarily because of the curvature term, and therefore I can integrate this to get, if I integrate it once, I get and integrating twice, so I've got the velocity profile. The velocity profile is not constant, but it's a parabolic shape. Okay. Now we have to satisfy some conditions for this to determine these constants. The first condition is, at the wall, at y equal to 0, the velocity is u naught. That's the velocity of the plate. Remember, y equal to 0 is on the plate. The second condition is, at y equals h of x, the tangential stress is 0, that is du by dy is 0, and this gives me, the first condition gives me the constant c2 to be u naught, and the second condition gives me the constant c1 to be 0, and therefore the velocity profile in the dynamic meniscus region is u of y will be u naught. So to arrive at this equation, I have taken into account the x component of the momentum equation and the normal stress balance at the interface, again in the dynamic meniscus. Okay. Now let's determine the mass flow that is flowing through. Mass flow rate, this again would be m dot, this would be density times 0 to the interface, from the plate to the interface, u of y dy. So in other words, I am trying to determine the velocity, the mass flow rate passing through because of this velocity profile u of y depicted in the dynamic meniscus. Again, remember, this is mass flow rate mass flux per unit depth. Okay, and this quantity we know, if I substitute the expression for u of y in this expression and integrate it, I get density times, I get 1 by mu dp by dx, I get h cube by 3 plus u naught into h. Okay, from mass balance which says m dot in the dynamic meniscus should be equal to m dot in the thin film, that is in the coating. Okay, and this therefore gives me density times 1 by mu the mass flow rate going through the coating we've already written down as u naught into h infinity times h, that's written here. Okay, and I can cancel rho on both sides and rearrange the terms to get dp by dx, the pressure gradient in the dynamic meniscus, h. Okay, but we know the pressure gradient is nothing but capillary pressure gradient. This pressure gradient is because of curvature, so that's gamma times hxxx, that is third derivative, and if I substitute this, we get gamma times hxx is mu u naught by h cube h infinity minus h, and this gives me the following equation: 3 times capillary number, mu u naught by gamma is capillary number, times h infinity minus h divided by h cube. This equation is called the Landau-Levich equation. This involves mass balance, the continuity equation of mass balance, along with the utilization of the x component of the momentum equation and the normal stress balance. Now, this is an equation to describe the thickness h of x in the dynamic meniscus. So this equation requires, it's a third order nonlinear equation, right? So to solve this equation, we require a few boundary conditions. As x goes to plus infinity, meaning you're well into the thin film, h goes to h infinity. Another boundary condition would be as you go into the thin film, it's a uniform thin film, so therefore the slope goes to 0. And another condition would be as x goes to minus infinity. Now this minus infinity has to be defined more carefully, but because of lack of time, I'm unable to go into details. But it essentially means as you go far away from the meniscus, dynamic meniscus, but downwards, the curvature dh by dx has to match, the second derivative, the curvature has to match the static meniscus curvature. So you are applying two conditions on one side, and then the other condition, the third condition, is at a different location of x. So this is a boundary value problem. So if you were to solve this boundary value problem coupled with the static meniscus shape, then you will get this number prefactor in the Landau-Levich equation 0.9458. Okay. So with this, our description on coating flows is complete. And we will now look at jets in the next lecture. Thank you.